What did we discuss last class? Anybody?
It's an amplifier.
Right. We started looking at amplifiers. In particular,
Op-amp.
voltage amplifiers, right? All right. Yeah, we'll come to the op amp later. Okay. And amplifier is a two-port system. It's got an input port and an output port. The input is some voltage, output is some voltage. This is an amplifier. And your output voltage is simply some G times Vi, where G is your gain. What are the ideal characteristics of an voltage amplifier?
Input impedance is high,
Input impedance
output
is...
impedance is low, and gain is infinite.
No, yeah, okay, we'll come to that. Again, as I said yesterday, for a voltage amplifier, G is not infinite. That's not what we desire. G is whatever we want it to be. Okay. For the op amp, it's infinite because it offers some other advantages. But for a general voltage amplifier, G is some fixed value, whatever we want. And ideally, it should be independent of the frequency of the input. But in terms of the ideal features, these two are the most important. And why do we want this? Why do we want infinite input impedance and zero output impedance?
For loading effect.
Okay, to avoid. Is it enough if we just have one of these characteristics? Let's say Rn is infinity, well, R out is definitely greater than zero.
So if the any other device is connected in the right side, then
Yeah, that's right. So then it will be a problem. Similarly, if R out is zero, but R in is less than infinity, then still this is a problem because you will load the input side. In this case, you load the amplifier's output side. Okay, so both these are, required for an ideal amplifier. Okay. Then we looked at this is again a special type of amplifier, voltage amplifier, represented by a triangle like this. It's got two input terminals. The output is drawn as if there is only one terminal coming out. The other terminal is assumed to be some ground. N Vp, and this voltage here is V out, which is some G times Vp minus Vn. Okay. And Vp and Vn are basically voltages measured with respect to the same ground as here. Right. So in the case of op amp, what are its ideal characteristics? And again, Rn, so we called it Rd, infinity, Ro, 0. And what about G, the gain, open loop gain of the amplifier, op amp? This should be infinity. And why is that? Why did we want, especially for the case of the op amp, why do we want this to be infinity?
we want the input output relationship to be independent of internal circuitry, sir.
Right. So we, by having this gain to be large, we saw that if you now implement a feedback circuit like this, negative feedback circuit, this is your input, this is your output. then the relationship between your input and output is approximately equal to 1 by h, which is only determined by what is connected in the feedback path. Right? If that is the case, then if your G is infinite, then by building feedback circuits with the op amp, the input output characteristics of that circuit will only depend on the components that are connected outside the op amp and not by the op amp itself. Okay, that's why for the op amp you want G to be infinite, but for any general amplifier you simply want G to remain fixed or constant. But this you definitely want the input being impedance being infinite and the output impedance being zero. And what is the equivalent circuit for an op amp? In fact, or any voltage amplifier for an ideal voltage amplifier. So this is for a general amplifier. It's like this. So this is VI, G times VI, Z0. Oh. In the case of the op amp, this is grounded. That's all. And this is your Vn. This is your Vp. Your Vi is simply Vp minus Vn. Okay. And then we looked at two circuits, right? The op amp. What is the first one?
Non-inverting amplifier.
All right. What is the circuit? So how is this connected now? What are all the things that are connected and what are they connected to? So this we know
There are
is
two
V out.
resistances.
Sorry?
There are two resistances, sir. One is connected to the ground and the input negative input side, and
Okay, there is
uh,
one resistance here that is connected to the ground. There is one here. What about the positive side?
positive side is connected to
This is connected to here. Okay. And what is the relationship between V in and V out? This is R1, 2.
V out equals to 1 plus R 2 by R1 into V.
That's all. And now here, uh, again, this is derived based on the assumption that Rn infinity or RD is 0 is infinity. Okay, and that's a reasonable assumption. And in reality, if you build a circuit like this using a real op amp, V out will in fact be more or less quite close to 1 plus R2 by R1 into VA. And what so now if you consider this entire circuit with the op amp and the resistors as an amplifier, one terminal is grounded, this is V in, this is V out, and the other terminal is grounded. This is the non-inverting amplifier. What is the gain of this amplifier? So basically,
Not by V.
it's 1 plus R2 by R1. What is the input impedance of this amplifier? Of the non-inverting amplifier.
infinity, sir.
Sorry?
Infinity, sir.
Yes, infinity. What about the output impedance of this amplifier? So
Zero.
this is R in, this is R out, is 0. So this is a pretty good amplifier. It satisfies all the properties that we want to, assuming that the op amp has infinite impedance. If the op amp has finite input impedance and finite output impedance, uh, but let's say the input impedance is high and output impedance is low, the non-inverting amplifier would still have a high input impedance and low output impedance. All right. What about the next circuit that we discussed?
Voltage follower.
Next one we looked at was the voltage follower. And what is the connect? How are things connected here?
The negative input side is connected to the output side.
What is V out in terms of V in now?
V out equal to V in, sir.
In, and again here also.
One.
And what is the use of something like this? Why? I mean, if V in is going to be V out, then what is the purpose of this?
So it acts like a buffer. So if there is low input impedance, so if we add a voltage follower circuit, it gives high input impedance.
Sure. So if you have a sensor that has a low, so which is giving you some output, and let's say it has high output impedance. Okay. Then if you connect, let's say they ground this, then see this has our sensor out is greater than zero. But this, if you connect the buffer amplifier, so now a poor sensor with a buffer amplifier will actually, when I say poor, the sensor is poor in terms of its output impedance. Otherwise, let's say it's a good sensor in terms of generating a voltage in response to the measurement, but it's got a poor output impedance. But if you connect the buffer now, after the sensor, and now the sensor plus the buffer will act like a very good sensor in terms of its output impedance. Okay. Similarly, if you have some device to which you need to connect your sensor, but let's say the device has fairly low input impedance, and if you put a buffer here before the device, then this would act, this device in this full block would act as if it's got high input impedance. And this is where we stopped yesterday. Let's continue. Okay. We'll now look at another uh, common circuit that is used. This time, I'll let you uh, derive the input-output relationship. Here, this is called the inverting amplifier, and the connections here are slightly different. In the previous case, the input was connected to the positive terminal, and this end of R1 was grounded. But now we've grounded the positive terminal of the op amp, and the input is now given to the other end of R1. Okay. Now, if you draw the equivalent circuit, right? This is grounded. R1. Now, can you tell me what is R out? In terms of V in? Let's say Vn. So this is Vp. This is Vn. How did we derive it last time? If we are assuming an ideal op amp, if the gain is infinity, then these two terminals would be at the same potential. Okay, the positive terminal is now grounded, right? That means this negative terminal should also be a ground, and this is a virtual ground because this point here is forced to have the same potential as Vp because your op amp is assumed to have infinite gain and it's producing some finite output. Okay, so this is ground. What is the current flowing through the R1 resistance? Let's call it
V
I1.
in by R1.
So I1 will be V in by R1, and the input impedance of your op amp is infinite, so there is no current flowing into the input impedance into the op amp. So whatever is flowing through R1 has to flow through R2, right? If that is the case, now tell me then what will be V out?
IR into R2, sir.
V out will be, sorry, can you repeat that again? I could not hear you properly.
I1 into R2, sir.
Okay, I1 into R2. Um, what sign though? Here, V out is the voltage measured with respect to ground, right? And Vn is at ground, and the current is, so if you assume a positive value for Vn, right, the current is flowing from ground to V out. So what would be the sign of V out?
Minus.
Has to be negative. That means V out is at a lower potential than Vn. Okay. If the current is flowing like this, then the difference between this, the voltage difference is between these 2 points, 0 minus V out would be equal to I1 R2. So that's why you get V out equals minus I1 R2. Okay. And I1 is V in by R1, so we get minus R2 by R1 into V in. So this would be, is that clear? So again, you can do the same thing. You assume a finite output impedance, input impedance, and finite output impedance, and you can derive the whole thing. And you assume a finite value of G. You derive a more complicated expression, and then if you use a limiting argument where Rn is infinity, R out is 0, and G is infinity, then you will arrive at this expression. Okay. So here, this is called the inverting amplifier because of this negative sign. Whatever voltage you apply here, it's amplified, but it is also negated. The output comes out with the opposite sign of whatever is applied here. Okay. And unlike the previous one, this can act as both an amplifier and an attenuator. When would it act as an attenuator?
when R1 is greater than R2.
If R1 is greater than R2, then it would act as an attenuator. But if it's R2 is greater than R1, then it will amplify but still add the negative sign. Okay. So now, if we consider this whole thing as uh, an amplifier block, and this is the inverting amplifier. Now, now tell me what is R in for this circuit. Out. What is R in this case? How will you find out R in, the input impedance of this amplifier circuit? how did we, I mean, in general, if you have a two-port network like this, how do you find the input impedance?
Output side, sir, we are using open circuit voltage, full circuit current for input
All
side.
right, so that's okay. So in that case, what would be the output impedance in this case? So if you look at this, right, the voltage is being produced by this, right? So even if you short this voltage source will maintain that voltage across the short. So here, your output impedance would be 0. What about the input impedance then? How do you find the input impedance? See, the input impedance is simply the voltage at the input terminal and the current that is flowing in, right, or flowing into the circuit, right, from your input source. So here, if you look at the circuit, right, V in is connected here. The other terminal is grounded. What is the current that is flowing in? This is the voltage with respect to ground. What is the current that is flowing in? It's this I1, right? There is a current I1 that's flowing through this. And what is I1? V in by R1. That means the input impedance is R1. Yeah? Is that clear?
No, sir.
Okay, all right. So if you're not convinced, okay, let's do this. Let's analyze the same circuit again. What is the definition of the input impedance? It's usually often we forget the definition of something, and that can often lead to confusion, and you're not sure how to go about computing something. What is the definition of the input impedance?
So what is the resistance offered by the amplifier in the input side?
Right.
When-
Correct. Okay. How would we find it out? So, if the model of the amplifier is like the model of the amplifier is always like this. This is see. Always keep this in mind. If you talk about an amplifier, this is the general model for the amplifier. This is your Rn, this is your Rout, and this is G is your the gain of your amplifier, and this is your V in, this is your V out. So now, in the case of the inverting amplifier, what is the circuit? What is the circuit? All right. If that is the case, right, here, how would you find what is the relationship between Rn and Vin? See, if there is an input voltage that you apply across the input terminals of your a voltage that you apply across the input terminals of this amplifier, and there is a resistance Rn, then there should be a current I in that's flowing into the amplifier, and that will simply be I in into R in, right? That means your
Yes,
R in, you can find out R in by simply applying an input and by observing the current that is flowing from your voltage source into the amplifier. Yeah?
yes, sir. Yes, sir.
All right, okay. If that is the case, now tell me, in this case, in the case of the non inverting amplifier, what is the input impedance? Now the equivalent, so the equivalent circuit for your This was your plus terminal, this was your minus terminal, this was R2. This was your op-amp circuit, but if you think of the whole thing as this whole thing is your inverting amplifier, then that block is simply like this. The positive terminal is grounded, one terminal is grounded, with your V in, the output is also grounded, one terminal, and this is your V out. And the model of the circuit is like this. Some G times.
Input and impedance will be R1, sir.
Yes. So now the way you find the input impedance is connected some V in, and you look at the current that flows into this. The current that flows into this is some I1, and that I1, if you go to this circuit and find out what that I1 is, that's simply V in divided by R1, because this terminal is at virtual ground. So the input impedance is R1. Why was the input impedance infinite in the non-inverting case?
Because the other terminal was given input and R1 was connected to ground actually. So,
No, yeah, here. This is the connection. Because the amplifier is assumed to have infinite input impedance, there is actually no current being drawn from your input source into the op amp. That's why your non-inverting amplifier had an infinite input impedance. Whereas in this case, has a finite input impedance because there is some current being drawn by this R1. Even though your op amp has infinite input impedance, the way things are connected here makes it look as if this circuit has a finite or makes this circuit behave as if it's an amplifier with a finite input impedance. Okay, so if you're still not convinced, right, or okay, you can then instead of following this argument, you can do this. You take your inverting amplifier, okay, this is R1, this is R2. If you had an amplifier with a with the input impedance that was not infinite, then whenever you connect a real voltage source on this side, like this, a real voltage source is some ideal voltage source in series with some uh, resistance Rs. This is your Vin. If you now connect this to this, right? Tell me what will be the out. And as far as you're concerned, this is your voltage source. This is your Vn. But the real
in,
Vn, sorry, yeah, go ahead.
in the place of R1, sir, will be having R1 plus RS, sir.
Right. The output that you will get will be minus R2 by R1 plus Rs into Vn. And this term here is less than R2 by R1. That means the output is not, let's say R2 is selected to be 10 and R1 is selected to be 1. So V out will not be equal to minus 10 times V in, but it will be some value. So the absolute value of the gain will be less than 10. Okay, that means even though the true open source voltage of your of this voltage source is V in, the output that we see is not amplified to the same extent. That's because there is loading caused by your amplifier. That means your amplifier must have a finite input impedance. But in the case of the non-inverting amplifier, even if you connected a real voltage source with some finite input impedance Rs, because this op amp, we assume the ideal op amp as, with infinite input impedance, the output that you see will still be V out equals 1 plus R2 by R1 into Vs or Vin. That's because this has infinite input impedance. It does not matter what the output impedance uh, of your voltage source is, because this has infinite input impedance. You don't have any loading. Okay. All right. So that way, the inverting amplifier allows you to change signs, but it's not ideal in the sense that it does not give you infinite input impedance. There are lots of other circuits that you can build. You'll have some of these in your assignment. So we'll not look at any other circuit at this point, except for one more, which is uh, called the instrumentation amplifier. This is an amplifier that is used for amplifying difference between voltage at two terminals, and this is called the 3 op amp instrumentation amplifier. There is also a 2 op amp version, but this is the most popular version. Again, the circuit, maybe it looks a little complicated, but if you go through the procedure of assuming these 3 op amps to be ideal and do the derivation, you should be able to arrive at this expression without any trouble. Okay, so the gain of this instrumentation amplifier is given by this expression. This is your gain, and V in is nothing but the difference between V plus and V minus, and V plus and V minus are reference with respect to some ground, and V out here is reference with respect to the same ground. Okay? And we will often make use of the instrumentation amplifier for many amplification applications in our course and in your lab as well. Okay. All right. So this is something you should be comfortable with and understand how this works. So that's the instrumentation amplifier. Look at one more characteristic of an op amp. There is often or there is an important characteristic when dealing with recording biopotentials, potentials from the body. Okay, this is called the common mode rejection, and the parameter that is used for describing this ability for rejecting common mode signals is called the common mode rejection ratio. Okay, now when we talked about the op amp, right? Even if you consider just the open loop op amp, this is Vp, this is Vn, and we said V out is simply the open loop gain multiplied by Vp minus Vn. That means your op amp is really a differential amplifier in the sense that it takes the difference between the voltages at its the two terminals, at the positive and the negative terminal, and then applies a gain of G and then produces an output. Okay, that means if I take an op amp and I apply an input where Vp equals Vn, what should be my output? It should be 0, right? Because Vp equals Vn. This is how an ideal op amp should behave. But it turns out, uh, again, because of the imperfections in the internal construction of your op amp, it turns out that if you take a real op amp, okay, and you connect some signal source, V in, and you apply the same voltage to both Vp and Vn, and you observe the output. If this was an ideal op amp, right, then V out should be uniformly 0. But it will turn out that V out is not 0. You will have some non-zero V out. Okay, that is related to V in. Right? Let's say that is some V out. There is some GCM common mode into uh, Vn. This is what you will see in a real op amp. But what we would ideally like to have is this VCM, or the common mode gain, V0. And for a real op amp, we quantify or we measure the ability of an op amp to reject a common signal that appears at both its input terminals by this parameter called common mode rejection ratio, or CMRR. So whenever you take the specification for an op amp, you will often see the CMRR being mentioned for an op amp, and you ideally want the CMRR to be very high, because the CMRR is defined to be so this G, let me call it OP, which is the open loop gain, divided by, so it's the ratio of the open loop gain of the amplifier divided by the common mode gain. And again, this is often described in dB. So you take the 20 log of this and then multiply by 20. So your CMRR is usually defined by, in terms, is given in terms of dB. This is basically the open loop gain divided by the common mode gain and the decibel value of that. Okay. Now let's do this. Let's say we have an input signal like, we're applying 2 volts here, or let's say 2 volts. We are applying 2 volts here, and we are applying 1 volt here. This, let's assume this is some real op amp. Okay. And I tell you that the open loop gain of this op amp is 10 power 6. Okay. How much will that be in dB? The open loop gain of this op amp.
Log 6,
Sorry,
6.
120.
120. Because it's 20 into log of this number. Right? Okay. Now, if you look at this signal, right, there are two components to this signal. Right? One is the difference between these, because the output of the op amp will depend on two things, right? If it's an ideal op amp, it will only depend on one thing. That is the difference between these two voltages. That means effectively the output that you see should be 1 times 2 volts minus 1 volt. So it should be G into 1 volts. So that's the output you would see. Because the gain is very high, you should see 10 power 6 volts. Okay. But there is also a common component between these two, right? Between these two, there is a common voltage of 1 volts, right? Both of these are receiving 1 volts, and the difference between them is another 1 volt, right? That means there is a common mode. So if you can say there is a differential voltage VD of 1 volts applied to this op amp, and there is a common mode signal of 1 volts being applied to this. The common mode signal is basically uh, the common voltage that is applied to both of them. Yeah, is that clear?
Yes, sir.
Okay, now the common mode voltage is 1 volts, the differential voltage is 1 volts. So if you only consider the open loop gain, then the output because of the differential input is G into 1 volts. And then I tell you that the CMRR for this particular op amp is 80 dB. Okay. Using this, can you now tell me what will be the actual output of this op amp? Because there will be a contribution from your differential input, which is G times VD. There will also be a component from G times GCM, common mode, into VCM. Now this we know because we know the open loop gain. What will be this if you're given the common mode rejection to be 80 dB?
Common mode gain will be 100.
Sorry, yeah, go ahead. Yeah. What is the common mode gain?
100.
100. How did you derive that?
Equating CMR is equal to the 20 log 10 G open voltage by common mode gain.
Okay. So we get 4. Sorry. Means 4 equals log 10 G by GM. Okay. That means this means G by ACM is what? What is this equal to?
10 power 4.
10 power 4. Your G is 10 power 6. That means your GCM has to be 10 power 2, which is 100. Right? So your common mode gain is 100. So now tell me what will be the output. So the output will be VD is 1 volt, VCM is 1 volt, so G is 10 power 6. So it will be plus. What will be the contribution because of this term? It will simply be
100 into
GCM.
1.
Sorry?
100 into 1, sir.
Yeah, so it will be 100. So the output will simply be, if both of these were in microvolts, right? 2 microvolts and 1 microvolt, then what would be your corresponding outputs? GVD will be 1 volt plus what will be the contribution of this?
0.1 volt.
It will be the output that you will see will be 1.0001 volts. Okay. Whereas if the common mode rejection ratio was infinite, okay, so instead of 80, let's say the common mode rejection ratio was 20. What will be the output in that case? Let's assume the input is 2 microvolts and 1 microvolts respectively. What will be the output in that case? So differential output will be the same, 1 volt plus what will be the contribution from your common mode gain.
0.1 volt.
Will it be 0.1? Why will it be 0.1?
It would be 10 power 5 into 10 power minus 6.
Okay. Sorry, it will be 10 power 6. No, it's 20. The common mode rejection ratio is 20. Yeah, I'm sorry. Yes, you're right. Yes. So it will be 10 power minus 5. No, sorry. What did you say? No, it must be 0.1 volts. So it will be 1.1 volts. Right? So low CMRR means your output is now affected by the common signal that appears between your appears across your positive and negative terminals. But if my CMRR was say let's say 200 dB, then this would be even lower. It will be even closer to 1. Okay. So CMRR is another useful property. See, a place where this becomes useful is if you're recording, let's say, from somebody's body. Right? Let's say you're measuring muscle activity, uh, and your body is a good pickup point for your 50 hertz noise. So that 50 hertz noise enters both your through both these electrodes. So if you have an op amp that does not have good common mode rejection ratio, then at the output you will have the 50 hertz noise appear. But if it has very high common mode rejection ratio, then the contribution will be very small. Yeah. So this is a very important parameter for an operational amplifier. All right. That's all I wanted to say about op amps. Now we'll move on to we'll quickly look at frequency selective filters. Uh, See, we discussed when we were talking about linear time invariant systems that LTI systems can be used for implementing frequency selective filters. Right. So, for example, let's say this blue signal is the signal that you've recorded from a sensor, right? And if you now take the look at the spectrum of the signal, let's say it looks like this. If you take the spectrum of this blue signal, it'll look exactly like this graph that's shown here. And let's say you know, and this is sorry, this is not time, this is frequency. Let's say you know that the signal of interest is between 0 to let's say 70 hertz. Okay, this is the signal. Everything outside is not related to your signal. Right? That means you're saying your signal is this slow varying component, and whatever you have on the signal that's varying very fast is really not of interest to you, and that's basically this high frequency component because it's varying very fast. Now, one application of LTI systems is that you can design an LTI system such that if you take the signal and pass it through that LTI system, that then the output signal that you get will be this gray signal that you see. Okay, I don't know if you can see it properly. Right? Basically, the output signal that you will get uh, will from the LTI system uh, will effectively only contain this component and not have this component. So your LTI system has basically passed everything from 0 to 70 hertz, and it's rejected things outside of the 70 hertz. So you end up getting this underlying clean signal or relatively clean signal. You cannot, of course, remove it completely in practice. So you can implement LTI systems that will give you this black signal when you pass your original signal through this LTI system. That's because your LTI system is acting as a frequency selective filter. In this particular case, you've designed it so that frequencies from 0 to around 70 hertz are passed through without major modifications, and everything outside of 70 hertz is attenuated. For example, the frequency response of your LTI system could be like this. So everything in this region is passed through, and everything beyond, let's say, this point is attenuated and made very close to zero. That's one of the major applications and the common application of LTI system. And again, you are familiar with this. There are four general types of filters that we can talk about, depending on the shape of the magnitude response of your LTI system or your filter. A low pass filter would be a filter that allows all frequency components from 0 to some maximum frequency and rejects everything beyond that maximum frequency. Okay, that would be a low pass filter. And the opposite of this would be a high pass filter, where the filter rejects everything from 0 to a particular frequency and allows everything above that particular frequency. A band pass filter is a filter that only allows a range of frequencies within a band between, let's say, omega 1 and omega 2, and everything else is rejected. And a band stop is the opposite of band pass. Everything in the band omega 1 to omega 2 is rejected, and everything else is passed through. And we'll often make use of the high pass, low pass, and the band pass filter. And the band stop, a special type of band pass filter, is your notch filter, which simply removes one particular frequency component and lets most of the other things through. Right? You would use a notch filter whenever you want to remove, let's say, the 50 hertz noise that still gets into your instrumentation. That's a common example of a band stop filter that is used in applications. And we already saw this. We can build uh, filter circuits using the passive components, resistors, capacitors, and inductors. Do you remember what kind of filter this is? The first one.
Low pass. Low pass.
This is the low pass. What about this? This is the high pass filter. And we derived the frequency response of this couple of classes back. So this is one way of building analog filters, right? But it turns out that these have some disadvantages. For example, if you think of this as a block, right? Some filter block. It turns out that if you just use a RC network like this, it has very poor input impedance and very poor output impedance. Okay, same here. So if you simply use these, then these blocks will load whatever it is connected to, and they will get loaded depending on what is connected on the other side. Right? So to address this problem, we will often use active filters. Active filters are simply filters that are built using active components such as op-amp, and often these days it's often just using an op-amp. So there is an op-amp that is used, and then the external components that are connected to the op-amp are chosen in such a way that the input-output relationship of this circuit now either behaves like a frequency selective filter. The advantage of such a of an active filter is that here if you use an active filter, then you so if you want to build a low pass filter like this using an active filter, you can avoid any attenuation of the filter in the pass band. Pass band is the band of frequencies that are passed through by your filter, so you can avoid that. uh, because you're using an op-amp, you can build these circuits in such a way that you get good input-output impedance properties. That means you get good isolation and avoid loading. And another important useful feature of op-amps is that you can build uh, implement filters with very nice properties without the use of inductors. Compared to capacitors, linear inductors are hard to build. So if you use op amps, then by just using resistors and capacitors, you can build a wide range of filters with different properties. If you were to build a filter with just passive components, then to get certain properties in terms of frequency selectivity, you will have to use inductors. But if you use an active filter circuit, you can avoid the use of inductors and build everything using just resistors and capacitors. That's another advantage of going for active filters instead of passive filter. We'll not go into the details of any particular filter. There will be a lab component where you will try out different active filters. I simply show topology for a particular filter here. I can't remember the name of this. I think this might be the Sallen key. So there are different ways in which you can connect your resistors and capacitors to get different types of filters, and these are all and these different ways of connecting these elements are called topologies. And I think if I'm not wrong, this is called the Sallen key topology. Okay. This particular circuit here, the way it's connected here, will act like a low pass filter, and if you want the general input output relationship of this particular combination, let's say this is impedance 1, impedance 2, impedance 4, and impedance 3, the input output relationship in the frequency domain is given by this. Okay. Now here, if you simply substitute for Z1, Z2, Z3, Z4 to be these and derive HFS, then the HFS that you'll end up getting will behave like a low pass filter. Okay. And by simply changing Z1, Z2, Z3, Z4, you can get a high pass filter also with something like this. Okay. Again, we'll not derive this. I'm showing this here just for you to know that you can build circuits like this for implementing active filters. Okay. Um, Final thing that we look at is how to obtain the frequency response of a system. If you're so, for example, if I give you this, give you a filter circuit, right? And I say this is some filter, and I ask you, can you obtain, give me the frequency response of this filter? How would you do it? what is one way you would, or what is one experimental way of obtaining the frequency response of a filter like this? And I tell you that this is an LTI system.
So
See,
we can
yeah, tell me.
customize the LTI system. No, that or uh, open circuit that one will decrease the frequency maybe. Then when there will be no frequency, a low pass filter that will be the frequency maybe.
Okay, all right. So here, we know that if it's an LTI system, right? If you apply a sinusoidal input with some frequency omega, what comes out will be a sinusoid with the same frequency but different amplitude and phase. Right now, so if you simply apply different sinusoids, so let's say I apply different sinusoids for frequency from 0 Hz to some very high frequency, right? So I apply, let's say the red line is my input frequency, and let's say the blue curve is the output that I obtain from the system. Let's say this amplitude is 1, right? And the frequency is some omega. Okay. Now, if you simply measure this height, right, this is how much, because your input signal has amplitude 1, uh, the amplitude of the output signal will simply be how much your uh, how much the gain of the system is uh, for this particular frequency. Let's say we plot the magnitude of h of omega, right? So at omega, this height that you see will simply be magnitude of h of omega. So that will be somewhere here. So if you now apply different frequencies and obtain this height and plot them like this, and let's say you find something like this. So that's the magnitude response of your of this particular system or this system. How do you find the phase response from this input output graphs? Here, phase response is easy. Here, this is your original sinusoid, the red line, but the blue sinusoid, the output from the system, is not only has a different amplitude, but it's also shifted in time, right? So you simply measure this. If you take this as time t equals 0, this is some negative time delta t. This delta t can be converted into phase if you know the frequency of your original signal. Let's say the original signal had a time period of capital T, which was 2 pi by omega. Right? Now this time delay delta t corresponds to a phase delay of delta phi, is given by 2 pi into delta t by this will be omega this. Okay, and this will exactly be equal to the phase delay introduced by your filter. So now if you apply different input frequencies and measure this delay and compute the corresponding phase and you plot it here like this would be your phase response. This is your, yeah. So that's a experimental way of obtaining your the frequency response of an LTI system. You simply have to apply different sinusoidal inputs and find out how the phase and amplitude of sinusoid of different frequencies are changed, and you plot the frequency versus amplitude, frequency versus phase. Then you get the magnitude and frequency response of your LTI system. So if this is a low pass filter, the magnitude response would look like this. If this is a high pass filter, and if you apply different frequencies, then you would get something like this. If it is band pass, then it will be like this. If it is band stop, get response like this. These are all the magnitude responses. Yeah. All right. Okay. All right. So you will do experiments like this in the lab to find out the frequency responses experimentally for the different filters that you build or systems that you build. All right. That's all I wanted to say for module 2 of course on basic instrumentation. I've uploaded the lecture from yesterday online. I will try and upload this video today. And we will move to module 3 and start talking about specific sensors from